Hi everyone, welcome back. We are continuing our discussion on related rates and trying to solve a variety of examples. In the last segment, we did some distance rate problems and we got an introduction to a ladder for sliding down the wall type of an example. Here we're going to continue that example. This is a part B of the same problem. So let's restate the original question. So we have a 20-foot ladder that is leaning against the wall of a house and the base is being pulled away at a rate of 1 foot per second. So the xdt was given to us as 1 foot per second. And because the length of the ladder does not change over time, went ahead and put a 20 right there. I did not introduce a new variable such as z. It was not necessary and it would be more complicated and make the problem unnecessarily complicated basically. So put the 20 right in there from the beginning. And so in this part of the question, so remember in the last part we found dy dt. We used the Pythagorean theorem to do that. Now here they want to know the rate at which the area of the triangle formed by the ladder, the wall, and the ground changes when x is equal to 8 feet. So at what rate is this area changing, the area formed right here? So to be able to do that, we're going to need to begin with the area equation, but let's write down again what is given here. So we know the x dt is 1, and from the last part we know dy dt is negative 0.44. So we got that in part A. So we can assume that those two quantities are given, and we're going to find dA dt, the rate of change of area of the triangle with respect to time at the moment when x is equal to 8. Okay, so here, let's begin by writing the equation that relates to variables. To get dA dt, we need the area equation for a triangle. Area equals 1/2 times base times height. So 1 over 2 xy is the area. And this equation we're going to need to take the derivative of, and 1/2 is just a constant. You can pull it outside. So dA dt equals 1/2 times, okay, the product rule is necessary, right? So x times dy dt plus y times dx dt. At this point, let's see what's given. Okay, so we know x is 8, dy dt is negative 0.44. Now, y is a quantity that we got in the last part of the problem, but just as a refresher, so if x is 8 and the length of the ladder is 20, to get y you use your Pythagorean theorem, right, which states x squared plus y squared equals 20 squared. In this case, 8 squared plus y squared equals 400. And from there you can solve for y. Y will be the square root of 400 minus 64, or square root of 336. So at this point everything is known, right? We know x dy dt, we know y dx dt, and we put them in there to solve for the unknown, which was the rate of change of area. So we can do that by plugging in those numbers in. So don't forget the 1/2 that was up front. So x was 8, dy dt was negative 0.44, y we just got square root of 336 times dx dt, which is 1. So if you put all of those quantities into your equation and simplify, you will get dA dt. And when you simplify, please verify this on your calculator, that you will get approximately 7.4, and the units for area would be square units, so square foot per seconds. Okay, and in the last segment I promised you we would do an angle problem with regard to this ladder question. So that'll be our part C. We're going to find the rate at which an angle changes. And to do that, let me go to my slide. Okay, so if we call the angle theta the angle between the ladder and the ground, so we're going to need to figure out for this question, find the rate of change of the angle theta at the moment when x is 8 feet. So that premise has not changed. We just are, instead of finding the rate of change of y or the rate of change of area, now we're asked to find the rate of change of the angle. Again, the length of the ladder is given fixed 20. We can put that in there right away. So let's think for a minute. How could we find the rate of change of the angle? So first of all, what are they asking as a derivative? So that'll be d theta dt, right? The rate of change of the angle at the moment when x is 8. What do we know? We know dx dt is 1. And which equation would be a good one to use here? So one thing I'd like to take advantage of is the fact that I know this side of this triangle, and I'm trying to relate, if possible, x and theta and the hypotenuse, which is 20. So a good equation, and clearly you're going to need to bring in a trigonometric function, right, to bring theta into the equation. So which trig function would be relating the adjacent side to the hypotenuse? If you said cosine theta, you are absolutely correct. So cosine theta equals x over 20. So that will be the defining equation that we have. Cosine theta equals x over 20. And at this point, this is the equation that we're going to take the derivative of on both sides with respect to time. So cosine of theta, the derivative will be negative sine theta times d theta dt. And on the right hand side, I want you to think of this as 1 over 20 times x. So the derivative is like a constant times x. Keep the constant, differentiate x. It'll be 1 over 20 times dx dt. So if we simplify, so let's take the derivative of both sides. The derivative of cosine theta will be, first of all, I rewrote them, but I prefer the 1 over 20 times x version because it'll help me better when I differentiate it. So derivative of cosine is negative sine theta. Don't forget to multiply it by d theta dt, because just like in the past, theta is a function of time, and you need to multiply everything with the derivative of the inside, which is d theta dt. On the right side, that's 1 over 20 times dx dt. And from this point forward, it should be smooth sailing because we're just going to plug in dx dt is 1. The theta dt is what we have to solve for. Well, there's one more little trick there. What about sine of theta? Maybe not so smooth sailing after all. Okay, we need to figure out the value of sine theta. So let's go back to our equation. Actually, I'm going to go back to our triangle. Okay, so in our triangle, what we know is that at the moment in question, this side is 8, this side is 20, and I've already figured out from the past version of this problem, from part B or part A, that this side was square root of 336, right? You can use the Pythagorean theorem to figure that out, no problems. Okay, now I want to know what is sine of theta in this triangle. Sine of theta will be opposite over hypotenuse, so root 336 over 20. So that's one little bit of detail there we're going to have to put in, and then it should be smooth sailing. So d theta dt is unknown, but that's a healthy unknown because we're solving for that. It's okay to keep it there. 1 over 20 was there, and dx dt was 1. So putting all those variables in their proper places, and to solve for d theta dt, you need to get rid of this. So I would say multiply both sides by the reciprocal of this, which is negative 20 over root 336. So d theta dt equals 1 over 20 times negative 20 over root 336. And I pull the negative outside here. You can do that. Now notice the 20s are canceling, and we're left with negative 1 over root 336. You can always convert that to a decimal. Please use a lot of decimal points, especially when you're entering answers into a platform such as Edfinity. And then the answer, the theta, always automatically will turn out to be in radians per second, because the understanding is when you differentiate, let's say, trig functions, there the understanding is that theta is in radians. Otherwise, the derivative would not have been so simple. There would be like a factor of like, pi over 180, something like that. So when we differentiate a trig function, we made an assumption that theta is in radians. So when you solve for d theta dt, it'll always turn up in radians. So let's review this question fairly quickly. It was very similar to all the other problems. The only difference is an equation that relates the variables was an equation that had theta in it, a trigonometric function, right? In that situation, when you differentiate both sides, Don't forget, derivative of this side will be negative sine theta times d theta dt. If you forget that, you'll say, okay, what am I solving for? There is nothing to solve for, and it'll be a problem. And on the right side, it was 1 over 20 times dx dt. From there, we just plugged in what was given, and we had to figure out what sine theta was for the situation to finish the problem. Okay, we're going to solve one last example using this will be another example on determining the rate of change of an angle. And give me one moment. All right, and here's one more example involving the rate of change of an angle. In this situation, we have two walkers. A is walking towards an intersection at a rate of 2 meters per second, whereas B is moving away from the intersection, going towards north. So maybe I'll add it's going north. At a rate of 1 meter per second. So X is approaching at a rate of 2 meter per second. And because that distance is getting smaller, you might represent it as negative 2 meter per second. And whereas B is moving away, so that distance is getting bigger, so you might represent it as positive 2 meter per second. Wait a minute, what did I do there? Let's see, A is approaching at a rate of 2, B is moving away at a rate of 1, so this should be 1 right there, 1 meter per second, and that's positive. Okay, at what rate is the angle theta changing, and when A is 10 and B is 20 from the intersection? So they want a rate of change of theta, that's d theta dt, right? At the moment when X is 10 and Y is 20. And what's given is the rate of change of X and A and B, which I represent the horizontal distance X. So the rate of change A is moving, I'm going to represent as dx dt at negative 2, and dy dt is positive 1. So given, goal, and now we need an equation that relates the variables. To find that equation, something that has theta in it, right? Now notice here everything is changing, x, y, and z. Unlike our ladder problem where one side was constant and it was advantageous to use that side, here there is no constant side. Everything is changing. So you could use any one of the trig functions. However, since we have so much information about the horizontal and the vertical side, meaning adjacent and opposite sides, let's think of which trig function relates theta to opposite and adjacent sides. And if you said tangent theta, you are correct. Tangent theta is y over x. That will be the easiest one to use for this problem. And what are we going to do with that? So as is typical, we're going to differentiate it with respect to the time variable. So differentiating the left-hand side, we'll get secant squared theta d theta dt. On the right-hand side, we must use the quotient rule. They both depend on time, so both are functions of time. So it'll be x times dy dt minus y times dx dt, everything divided by denominator squared, x squared. And let's see which ones of these quantities do we know that we can substitute. We know x is 10, y is 20, dy dt is 1, and dx dt is negative 2. So those I can plug in right away. So x is 10, so 10 times 1 minus y is 20. 20 times the dx dt will be 20 times negative 20. And everything divided by x squared, so that will be 10 squared in the denominator. On the left-hand side, we don't know yet what secant squared theta is. That we're going to have to figure it out. But recreate that triangle at the moment in question. X is 10 and y is 20, right? Z is unknown. We can figure out z, which is going to be the square root of 10 squared plus 20 squared, since that's the hypotenuse side. So you can figure it out. It'll be square root of 500. So from there, if this is square root of 500, what is secant of theta? And I can actually simplify that as 5 times 100. 100 comes outside as 10, so that could be like 10 times the square root of 5. Okay, to find secant of theta, let's remember, what is secant in general? It's 1 over cosine, right? Also known as hypotenuse over adjacent. Okay, so hypotenuse side is this, and adjacent side is that, right? So if I take the ratio of 10 root 5, so secant theta equals 10 times the square root of 5 divided by, so that's the hypotenuse, divided by adjacent side, we're going to get square root of 5. So go ahead and plug that in here, except notice this is being squared, right? So you're going to square the square root of 5, and that will end up being 5, square root of 5 squared. And the only unknown is d theta dt. We can certainly solve for that. So you would first simplify your numerator. Don't forget negative times negative is positive, so you got 40 plus 10, which is 50 over 100. And then you're going to divide both sides by this quantity, which equals 5. So d theta dt equals, so the top was 50, bottom 100. And remember, we divided by 5, so we have the 1 over 5 up front. So now 50 over 100 is a half. So you have a half times 1/5, which is 1 over 10, or just 0.1. And the units, remember, for rate of change of angle problems will always be in radians per unit of time. Here time was in seconds, so radians per seconds is the rate at which the angle theta is changing. So I realize that the angle problems are a bit more challenging than everything else, mainly because students tend to be a little bit weaker on their trigonometric knowledge, and it makes it, for that reason, I think, a little bit more challenging. But if you do like 2 or 3 questions of that type also, you're going to find that you're getting a lot better. They're not that much more difficult. It's just, I think, once with repetition, just like anything else in math, right? With repetition, I think you're going to be able to do them just fine. And one thing I would highly recommend is for the last 2 questions that we solved, if you were watching the video, now can you close your notes and redo them, and this time completely on your own. And that way you'll build confidence that you can do these angle questions, and then go back and find a couple of those unsolved ones in your group activity or your assignment, and then go ahead and solve those as well. All right, so I know this is overall a challenging section, so hang in there. The time that you spend solving challenging questions, really helping you develop your brain, helping you develop problem solving skills, it's time well spent, because if everything was so easy, it's like developing, when you go to the gym and you want to build muscle, you want to have some resistance, right? The same is true about learning. So sometimes the more challenging topics actually help you learn more and become better and stronger math students. So good luck with it, and if you have any questions, please contact me.